Welcome to Edunguru students. In today's session we will be discussing about Maxwell's equations and we will see whether these equations are valid for an electromagnetic wave or not. Let's see what are the Maxwell's equations. It's Maxwell's equation and plane electromagnetic waves. This is what we will be discussing today. The fundamental equations in electricity and magnetism are, so Gauss's law for electricity is the first fundamental equation which we learned in electrostatics, and this is given as E dot ds, that is the closed surface integral is equal to q enclosed upon epsilon naught, right. The second expression is Gauss's law for magnetism. It is given as integral of B dot ds is equal to 0, right. This is the second equation. The third is Faraday's law, and this is given as the line integral of E dot dl is equal to d phi b upon dt with minus sign, right. That is the negative of rate of change of flux is equal to EMF induced across the loop. So this is the Faraday's law, and the fourth equation is of Amperes law. The expression for this is line integral of B dot dl is equal to mu naught IC, this is the conduction current, that is because of the flow of charges, and equal to, this is equal to mu naught epsilon naught d phi E by dt. We have already learnt about this. This is the displacement current ID, right. So this is the Ampere circuital law. All these four fundamental equations taken together are called Maxwell's equation, right. Collectively these equations are called Maxwell's equation. So let's discuss these equations in vacuum. In vacuum there are no charges. No charges, right. Therefore IC is equal to 0, right. Now this Ampere's law, which is given as B dot dl mu naught IC plus mu naught epsilon naught d phi E by dt reduces to, since this is 0, it reduces to mu naught epsilon naught d phi E by dt. This is B dot dl, right, in vacuum. And what about Faraday's law? The Faraday's law is E dot dl is equal to minus d phi b by dt, right. Now let's check whether these laws are valid for a plane electromagnetic wave or not. The equation of electric field is given as E is equal to E naught sine omega times t minus x by c, and B is equal to B naught sine omega times t minus x by c. The amplitude of the field is plus minus E naught and the amplitude of the magnetic field is plus minus B naught. It will vary in between this, right. So let's discuss first, let's see the application for Faraday's law. The electric field is along y axis and the magnetic field is along z axis. So Ey is equal to E naught sine omega times t minus x by c, and Bz is equal to B naught times sine omega times t minus x by c. Now let's discuss its validity for Faraday's law. This is y axis, this is x axis, and this is z axis, right? Let's take a loop here. Let's take a loop in the xy plane. The electric field here is along y axis, so this is Ey, or let's write it as E only, and the magnetic field is along z axis, this is B, right? This loop is A, B, C and D. This is at x is equal to x1. The length x AD is at x is equal to x1, and the length BC is at x is equal to x2. Now, in Faraday's law, what we have is integral of E dot dl is equal to minus d phi b by dt. So let's calculate the line integral of E dot dl, right? So the line integral of E dot dl is equal to integral from a to b E dot, let's say this length is L, it's E dot dl from a to b plus integral from b to c, it's E dot dl again, plus integral from c to d, it's E dot dl, plus integral from d to a, it's E dot dl, right? Now, the first case, AB is perpendicular to E, right? So, this term becomes 0 plus this E dot dl from B to C. It is along the direction of field E, right? The length is L. This E dot dl from B to C is E into L. This is at x2, right? So, let's write this as E at x2. E is at x2 into L. This is E as a function of the value of x will be substituted by x2 in this case, plus again this third term, that is E dot dl. Here also the dl will be making an angle of 90 degrees with the field, right? Again its value is equal to 0. So this is again 0 plus the last term will again be equal to E times x1 into L. This is E dot dl. Now, here this is cos of 180 degrees because the angle is 180 degrees. So, this is E of x2 into L minus E at x1 at multiplied by L. So, this expression is now E dot dl is now E naught sine omega times t minus x2 by c minus sine of omega times t minus x1 by c. This is E dot dl. So, we have calculated E dot dl now. Now, we will try to calculate this flux phi b, and then we will differentiate it to calculate the rate of change of flux because of the magnetic field, right? So, here you can see that magnetic field is along the z axis. So, let us draw this loop again and calculate what is the flux of the magnetic field. Let us say at a distance x from here, this loop, this width is dx, magnetic field is pointing towards z axis, right? The area vector of this small strip is parallel to the magnetic field vector, right? So, we know the length of this, it is L. So, the flux, we are calculating this, right? We are calculating flux phi b, the magnetic flux through this loop. Its d phi b is equal to b dot dA. This is We are assuming the angle between them to be 0 degrees. So, this is B naught sine omega times t minus x by c is multiplied to dA. This is L dx, right. This is the flux through this small strip which we have chosen as an element, right. It is through this. Now, we will integrate it in between x1 to x2. X is varying from x1 to x2. So, net flux phi b is equal to integral of b naught L sine omega t minus x by c into dx from x1 to, this is b naught L, the integral of sine is minus cos, and we are integrating it with respect to x minus 1 by omega by c. So, it is minus c by omega, minus minus becomes plus. This is cos of omega times t minus x by c. This is from x1 to x2. This is phi b. When we substitute the limits, it is b naught L c by omega cos of omega times t minus x2 by c minus cos of omega times t minus x1 by c. This is phi b. d phi b by dt, the negative of rate of change of this flux is, now we have to differentiate it with respect to time, right. So, differentiation of cos is minus sign and minus of minus is plus, and we have this negative of rate of change of magnetic flux is equal to, and this is b naught L c sine of omega times t minus x2 by c minus sine of omega times t minus x1 by c, right. Both the equations, both the terms are of the same equation. So, we can say that integral of E dot dl is equal to minus of d phi by dt only when E naught is equal to B naught times c, right. This is the condition for Faraday's law to be true for a plane electromagnetic wave. Now, let us check it for Amperes law. I will write the law first. It is in vacuum we are writing it, right. So, it is B dot dl is equal to mu naught epsilon naught d phi E by dt, right. This is the Amperes law in vacuum. This is y axis, this is x axis, and this is z axis. Let us take a loop in xz plane. So, we have taken this loop in the xz plane. Let us A, B, C, D. Here also this is the same loop. One diagram we will use it to find B dot dl, and the other one we will use it to find the electric flux. Right. The field is, electric field is perpendicular or towards y axis, and magnetic field is towards z axis, right. This length is, let us say this length is, so let us try to find out this loop integral of B dot dl. Here it will be from A to D, we are moving from A to D to C to B, and then again from B to A, right. Now, this A to D, this term will be B dot L, because both the magnetic field as well as the length are parallel to each other. This term will be equal to 0 because magnetic field is at 90 degrees with the length. From C to D, it's, let us write this as B1, this is B to L with minus sign here, because the angle between B and DL is 180 degrees. This is again 0. So, now when we substitute this, it becomes B naught sine omega times t minus x1 by c minus, it's B naught sine omega times t minus x2 by c. into L. So we have this loop integral of B dot dl. Now we have derived, or we have find the expression for the left hand side of this equation. Now we will try to find the expression for the LHS of this equation by calculating the electrostatic flux. So electric flux, right? So here we have this electric field E, which is towards y axis, right? This is y axis, this is x axis. So what we will take here is, we will take a small element, this distance is x from here, and the width of this is dx, right? So the flux is d phi A is E dot dA. Let us say the angle between E and dA is 0 degrees. So this is E, this length is L, right? So it is EL dx. Now let us substitute the value of E here. It is E naught into L, this is sine of omega times T minus x by C into dx. Now this, to find the net flux phi E, this will be integrated from x1 to x2. Clear? Now this is E naught L. When we integrate it, it's C by omega with minus sign, and integral of sine is minus cos, so this minus sign vanishes. We have this integration as cos of omega times T minus x by C. This is from x1 to x2. This is phi E. Now this is E naught L C by omega cos omega T minus x2 by C minus cos omega T minus x1 by C. This is phi E. Now let us differentiate it to find the rate of change of electric flux. So it's d phi E by dt is equal to minus E naught L C by omega into omega. It's sine omega times T minus x2 by C minus sine omega T minus x1 by C, right? This is d phi E by dt. When we multiply mu naught epsilon naught to it, this term becomes minus mu naught epsilon naught into E naught L C sine of omega times T minus x2 by C minus sine of omega times T minus x1 by C. So now we have LHS of this equation, right, that is B dot dl. Now we want to find what is mu naught epsilon naught d phi E by dt. So we have found mu naught epsilon naught d phi E by dt. Now let us compare these two equations. Here it is minus sign, if it gets absorbed inside, it becomes sine omega times T minus x1 by C minus its sine omega times T minus x2 by C, right? So on comparing these two expressions, what we get is B naught L, this B naught L is equal to, B naught L is equal to mu naught epsilon naught E naught C, right? So it's B naught L is equal to mu naught epsilon naught E naught C into L, right? This L cancels out from here. We have B naught is equal to mu naught epsilon naught E naught into C. This is, so Amperes law is applicable when B naught is equal to mu naught epsilon naught E naught times C for a plane electromagnetic wave. Faraday's law was applicable when E naught was equal to B naught C. So from these two expressions, that is E naught is equal to B naught C, and from this equation B naught is equal to mu naught epsilon naught E naught C, E naught is B naught C, right? So this is E naught is equal to B naught times C. Now from these two expressions, what we get is mu naught epsilon naught B naught C square is equal to B naught. This B naught cancels out. We have C square is equal to 1 upon mu naught epsilon naught, and this C is equal to 1 upon root of mu naught epsilon naught. On substituting the values of mu naught and epsilon naught, we have the values also, right? Mu naught is equal to 4 pi into 10 to the power minus 7 Tesla meter per ampere, and epsilon naught is equal to 8.85 into 10 to the power minus 12 Coulomb square per meter square Newton, right? When we substitute the values here, we have this C as 2.99793 into 10 to the power 8 meters per second, or it can be approximated as 3 into 10 to the power 8 meters per second, right? So this actually proved that light is an electromagnetic wave, right? So in this session, we have discussed about Maxwell's equation. We have seen the conditions for their validity for plane electromagnetic waves, right? We have derived the velocity of light using permeability in vacuum and permittivity in vacuum. In the next session, we will be discussing about energy density. Till then, thank you very much.
In this module, we have learned about Maxwell's equations. First, Gauss law of electricity. Line integral E dot dA is equal to charge inside upon absolute naught. Second, Gauss's law for magnetism. Line integral B dot dA is equal to 0. Third, Faraday's law. Line integral E dot dl is equal to minus d phi E upon dt. Fourth, Ampere Maxwell law. Line integral B dot dl equal to mu naught IC plus mu naught absolute naught d phi E upon dt. The condition for electromagnetic wave follows the Maxwell's equation is in Faraday's law E naught equal to B naught C, in Amperes law B naught equal to mu naught absolute naught E naught C, and at last light is an electromagnetic wave.